Hello, welcome students. Good morning, all of you. So this is our first video module on classical mechanics. In this video, we will be discussing some of the introductory topics which you had already learned in your degree classes. But these introductory sessions or topics will be of great use in our later discussions. Okay, when we go through other topics, advanced topics. So these topics ideas will be made use. So that's the relevance of the module one. Uh, uh, okay. So first, what is classical mechanics? The question arises. In degree classes, you usually study mechanics only, no classical mechanics. But here the mechanics is studied under the title classical mechanics. So what is mean by classical? So in fact, classical word is usually coined by people. Classical dance, classical music, okay, classical arts. So classical usually means something conventional or something old or something which has been there for long years. Okay. So it has some historical context. So same way here in physics also, classical mechanics means any mechanical theory, the theories on mechanics or theories of moving bodies, so which had been there for long years, okay, conventionally followed for last many years. Because in physics we have quantum mechanics, we have statistical mechanics, okay, we have modern mechanics. So that is why this part of physics is known as classical mechanics, something those theories and laws which are being studied or which have been practiced or followed or believed for the last many centuries, you can say. So those theories are summed up in classical mechanics. Okay, and we usually say classical mechanics deal with the motion of bodies. Okay, this motion uh, can be real motion or resting position, equilibrium under equilibrium forces. Two cases may arise. A particle may be moving due to some forces, or particle may be in equilibrium position due to forces. You know, when certain equilibrium forces are acting, a particle may come to rest, but that doesn't mean that particle is not experiencing any force. Even though there may be so many forces, but still motion may be impractical. For example, in a tug of war, when two teams are pulling a rope from each other, if they are applying equal forces, the rope may be in a stable position. The rope may not be able to move to and fro. So that's a good example for equilibrium motion. Okay. So such many physical examples we will quote in the later discussions of the topic. Uh, okay, so anyway, there can be a motion, there can be rest. Both are discussed in classical mechanics. Okay, and in classical mechanics or in mechanics, motion of the particles are dealt with, and were certain principles, theories, laws, okay, axioms, all are used. Okay, certain theories you can prove, certain theories you have to take as fundamental principle which cannot be proved, so that we call as axioms. And there are many laws, okay, because we know many motions are based or depends on many principles and laws, okay. And in classical mechanics has so many applications in different areas of science, okay, such as astronomy, you know, planetary motion we discussed, okay, many celestial motion we discussed, where classical mechanics or mechanics is required. In chemistry, they use mechanical theories in the discussion of dynamics of molecular collisions, okay, and properties of gases. This is also discussed on the basis of mechanical theories. And when you come to geology, where many things are discussed under mechanical theories, the propagation of seismic wave is one example, where wave motion of particles are used. Okay, wave theory of particles are used. And when we come to engineering, where so many things are there, so many things are there, numerable number of things are there. Uh, which are discussed using the theories and laws of mechanics. Okay, so this is the description here is limited. In fact, the role or the significance of mechanics is infinitely large, that cannot be discussed in one or two slides. Okay, so now, so if you go to the history of mechanics, it has been evolved through the pioneering works of so many people. Okay, so many people that involves philosophers, thinkers, priests, okay, mathematicians, many visionaries, okay, novel thinkers, and of course scientists. And you may be knowing in ancient times those pioneers were not scientists, or they were not professionals. They were simply preachers or all the ancient philosophers. They used to preach about many things, not only about mechanics, even biology, chemistry, astronomy, literature, philosophy, and in theology, and in many areas they used to discuss things. Okay. Okay. Now, uh, come to let us go through the pioneering works of some of the basic discoverers, or you can say some of the great luminaries in mechanics. One is Aristotle, one is Copernicus, Galileo, Kepler, Descartes. So this list is endless, in fact, but still it will be worthwhile to go through some of the main, okay, key personalities in mechanics. One is Aristotle. He is very famous philosopher from Greece. Okay, this is one of these theories, famous theory. An object's speed of fall is proportional to its weight and inversely proportional to the density of the fluid through which it is falling. So this is an old theory, and every school child know today that this theory is not valid. But this was the theory believed by people in those days. Okay, and nowadays the weight has nothing to do with the speed. Okay, if two bodies of different weights are dropped, they will fall in equal interval of time. Okay, so but in olden days they believe that weight has a role to play in speed, in controlling the speed. And he even put forward a theory. Suppose we launch an arrow from a bow. According to him, the arrow is moving ahead because of the push from the vacuum, push from the air. And we know now today that arrow is moving because of the energy stored in the arrow when it is thrown away, launched from the bow. But in those days, his theory was that arrow is simply moving because of the air pressure that is exerted on the arrow from the backside. Because when arrow moves through the air, a vacuum is created and air rush into that vacuum, and that air is pushing the arrow. That is why arrow is moving. That was the theory of Aristotle. And if you come to keep in mind that this is not the only theory by Aristotle. There are so many theories on many areas on physics, but still these are some of the worth mentioning theories. That is why I quoted here. Now come to Galileo, because one of the great visionary and you can say the real scientist of those times, who contributed immensely to physics. And it was he who introduced the ideas of speed, velocity, and he made the theory of free fall of bodies to Earth. And the initial concepts of relativity was given by Galileo, and inertia also that we study usually in schooling. And about many theories of projectile motion was also put forward by Galileo. And you may be knowing his invention of telescope and how he observed celestial bodies and made theories on planets like that. And here is now our Sir Isaac Newton. He was an English scientist, you can say, English physicist. Not only physicist, he was a mathematician too. And it was he who unified all the three laws of nature, or laws of motion, you can say. Even before the laws of motion was there, but in a scientific framework, it was Newton who compiled it. He introduced the ideas of force, how force can be defined, how force can be mathematically represented, and it was he stated that uh, if you know the force, total force or the natural force acting on a particle, you can predict entire thing. You can predict everything about the particle. Okay, I hope it is clear. If you know the force or the natural force acting on a body, you can predict its future course of motion. That was a very important concept in physics. Even today, it is valid to great extent, and we make use in many theories, not only in mechanics, even in electrodynamics, in plasma theory, statistical mechanics, even in quantum mechanics, many areas, this force concept is very good. And it was he who proposed the basic fundamental ideas of calculus. Okay, along with Newton, it was Leibniz from Germany. He also contributed heavily to calculus, and the concept of derivatives, integral, etc., were introduced in mathematics. And now comes the Leonardo Euler, an Italian physicist. It was he introduced the ideas of rigid body motion. Newton only talked about the particle motion, and it was Euler, he extended the Newton's theory to rigid bodies or large bodies or extended bodies. And Euler also talked about deformation of bodies, how body get to change their shape on application of forces, and the concept of elasticity and properties of classification of body on the basis of elastic property was one of the important idea proposed by Euler. And it was he made the relation between angular momentum and torque. This is an important concept in physics. You can say uh, laws of one of the important laws of motion is rotational motion. You can say Newton's second law in rotational motion, or you can say Euler's law of motion. It is also called Euler's laws of motion. Anyway, this theory will be studying in this module very shortly. And here comes now the next one. Joseph Louis Lagrange is family most renowned person with his book on analytical mechanics. Okay, this book was written by Louis Lagrange almost 100 years later by Newton. Newton wrote his book Principia Mathematica in 1640. Now, around 100 years later, Lagrange wrote the next book called Analytical Mechanics. And this book offered a comprehensive treatment of classical mechanics since Newton and formed the basis for the development of mathematical physics in the 19th century. Okay, and it will be interesting to know that Louis Lagrange gave a new method to discuss mechanical theory, the theories of mechanics, because Newton discussed everything in terms of figures, diagrams, and his theory was vectorial. But in Lagrange's theory, no vectors are required. Everything can be written in differential form, and theories can be well explained. And in mechanics, there is a separate branch of mechanics called Lagrangian mechanics. In Lagrangian mechanics, if you know the Lagrangian, is a mathematical function. If you know the Lagrangian of a function, the Lagrangian of a particle or a system, you can predict so many things about the system. You can predict so many things about the system. Just like in Newton theory, if you know the force acting on a particle, you can predict everything about it. Similarly, in Lagrangian, if you know the Lagrangian of a particle or a system, you can predict so many things. You can predict the future course of the system. Okay, that is the advantage of Lagrangian mechanics. Okay. And he had many other contributions like calculus of variations. This is of great use in our discussion too. And Lagrange equations of motion is another contribution. And it was he who theorized three-body problem. He could make theories on Earth, Sun, Moon system. Already two particle system were there, well explained theories were there, but it had its own limitations. But it was Lagrange who made a three particle theory. Based on that, he could explain the motion of Earth, Sun, and Moon. Okay, he could describe it well. That was another great contribution from the part of Lagrange. And here comes now one of the another luminary called William Rowan Hamilton, an English physicist. He was more a mathematician than a physicist, and the greatest contribution was by him was Hamiltonian, H of a system. Hamiltonian is simply the sum of potential energy and kinetic energy. Okay, if you know the Hamiltonian of a system, you know everything about it. Just like if you know the force on a body, you know you can predict so many things. Just like that, if you know the Hamiltonian of a system or a particle, you can predict so many things of it. And that is famous Hamilton's equation of motion, just like we have Newton's equation of motion, which can be used to discuss the motion of particles. And another great advantage of this Hamiltonian mathematics is that you can extend it to any other branch of physics, including quantum mechanics, statistical mechanics, celestial mechanics, okay, cosmology, electrodynamics. In all these areas, this find application. Unlike Newton theory, Newtonian theory you cannot use in certain areas of quantum mechanics, but Hamiltonian theory you can use in many other areas. So it is more, you can say, it is more advanced. Okay, so these are the contributions of Hamilton, and interestingly, you may be it will be fine to tell you that he was well versed with many world languages, including many Indian languages. He was well versed, and until his death, he could use those languages, and he could read many books from different languages. So he was such a great genius. And now comes the Carl Gustav Jacobi, or simply Jacobi. He was an Italian mathematician and a physicist, you can say. And he also contributed greatly to mechanics. And there is a famous Hamilton-Jacobi equation. This can be applied in many mechanical systems, dynamic system, and can be solved. And it was he introduced the concept of determinants in matrix. And another important contribution is the elliptical function and elliptical integrals in mathematics, which also find a great application theoretizing many classical mechanical theories. Okay, so these are some of the great luminaries in mechanics. We have not discussed exhaustively, but still we discuss many great ones. Still there are many other many worth mentioning people in mechanics. Those details you will definitely get from any sites that is left for you. Now comes to mechanics. It has three broader areas. First one is statics, which deals only with bodies at rest under some equilibrium forces, and equilibrium is related to forces. How it is, why it is in equilibrium, and what is the condition required to be in equilibrium? What's the condition to be followed by these forces? Okay, what is the condition to be followed by these forces so that the particle remains in equilibrium? Such conditions are derived in statics. Okay, great application in many areas. Then comes the part kinematics, another branch and areas of mechanics, where study of motion of bodies are done, and we don't think about the mass of the body, we are concerned more about velocity, displacement, acceleration, speed, like that. Okay, suppose when you write S is equal to ut plus half t square, where you relate displacement with the acceleration and velocity, where mass of the particle is not known. So we say that this area comes under kinematics. Okay. Now we have the third area, broad area, that is called dynamics, where motion of the bodies are studied and the force involved is also important. Okay. Where force involved is also what kind of force, whether it is a electromagnetic force or a gravitational force or any other sort of force, elastic force, like that. And depending on the type of force, the motion can be different, and where mass is also important, and where you can even predict the motion. Predict the motion means in future course of time, where the particle will be what will be position, acceleration, velocity, natural motion, like that. All are discussed under dynamics. Okay, so this way you can say dynamics is more comprehensive, more exhaustive or elaborative compared to statics and kinematics. Okay, so and now you know there are many conservation laws in physics. So many conservation laws. Conservation laws are very important in mechanics because it tells you that under certain conditions, certain things of a body remain constant. That is basically conservation. Under certain condition, certain things may be constant. Under certain condition, sometimes a momentum of a body may be constant. Under certain condition, the energy of a system may be constant. Under certain condition, the charge of a system may be constant, total charge. So accordingly, we have different types of conservation laws in physics. This is very important because every motion or every phenomena taking place in physics always obey certain conservation laws. Okay, without obeying conservation laws, nothing happens in physics. Nothing happens in physics. That is the importance of law. So if you follow conservation law, we can explore, we can derive many new information from different phenomena. So, in fact, there are 6 types of conservation laws. These are those 6 laws. Anyway, all these conservation laws we are not going to deal with, but some of the conservation laws we will be definitely making use in our future course of discussion, especially conservation law of linear momentum, conservation law of angular momentum, and conservation law of mechanical energy. These 3 will be definitely used in the present course, in the current course, and in many other areas. You may be seeing the conservation laws of baryons, especially in nuclear physics, conservation laws of leptons, and conservation laws of charge. Okay, so that is left for you. And now just briefly let us see what is conservation laws of linear momentum. Because you know in Newton's laws we talk about force equals rate of change of momentum, written as F equals dp by dt. And if you know that if your body is not experiencing any force, then you can say force is equal to 0. Force is equal to 0. Then what happens? dp by dt equal to 0. Then what happens? The momentum of the body becomes either a constant or a 0. If the body is moving, then you can neglect the 0 concept. Okay, 0 doesn't have any meaning, meaningless. So we say that momentum is constant, P is constant. So this is called the law of conservation of linear momentum. Or you can make it more generalized. You can say that for a system, if there is no external force acting, then the total momentum of the system will be always conserved. Okay, you can talk about a single body, a single particle, or about a broad, an extended system, maybe a celestial system of a number of stars and galaxies, or you can talk about a system of particles flying in free space. Or in any case, if there is no external force acting on the system, then total momentum of the system is conserved. Okay, that is the general statement for law of conservation of linear momentum. And you have the law of conservation of angular momentum. And you may be knowing what is an angular momentum. Suppose a particle is moving and suppose it is having a rotational motion, for example, with respect to a point, then it is having a angular momentum with respect to that point. Okay, you write if the particle velocity is v and its mass is m, then its linear momentum is p. And if the length of the position vector with respect to the reference point is r, then you can write the angular momentum as r cross p. Okay, this is a well explained idea in your UG classes, and this is not new. And of course, we have momentum equals mass times velocity, and if a body is rotating, then you have the equation for torque also. Torque is given by r cross f. Okay, then if you differentiate this angular momentum with respect to time, you can differentiate both sides. So what happens? You can expand the right hand side. If you expand the right hand side, you will get r cross dp by dt plus dr by dt plus p. And obviously dr by dt is the velocity and dp by dt is the force. Okay, dp by dt, rate of change of moment, the force. So we get dl by dt equals r cross f plus v cross p. Okay, so a slight modification of this equation. R cross f is torque, so we replace with torque, and p is momentum, mass times velocity, and here you have two velocity, the v cross v is coming, so that will be definitely 0. So you can write simply dl by dt equal torque. Okay, rate of change of angular momentum is torque. Now you know if torque acting on the body is 0, if there is no external torque on the body, then obviously the angular momentum must be constant. Okay, there is no other alternative because body is moving, so you cannot say that angular momentum is 0. That is a unrealistic case. So we get the case angular momentum is constant. So now we can generalize. How we can generalize? We can generalize that if no external torque is acting on a system, or if no external torque is acting on a body, then total angular momentum of the system or body should be a constant. And this is known as law of conservation of angular momentum. Okay, you have so many physical examples for it, and I am not going into that. You must have studied in your degree classes. You please refer all those concepts. Okay. Now we have another concept here: conservative force and non-conservative force. Okay, forces can be broadly classified in these two. What is a conservative force? If a force is conservative, then work done to move a body from one point to another point is independent of the path traversed. That is the requisite condition for a force to be conservative. Understand? That means whatever way you follow, you can take a body from one point to another point through so many paths. But total work done should be always a constant, irrespective of the path. Work done will be a constant. That is what is shown by these integrals. L, Q, P, etc. shows different path followed by the path used to move the body from one place to another place. So you can say that work done is path independent. In a conservative force field, work done to move a body from one place to another place, another point, is independent of path independent. Work done should be always a constant. Okay, so similarly, if you move a body from one place to another place, work done you can write integral 1 to 2 f here. Again, if you move from the second point to the first point, you will see that the work done will be negative in that case. Suppose the initial case you did work on the body to move from point 1 to 2. In the second case, you will get that work out of it. You will get that work out of it. So we can say total work done to move a body around a closed path is equal to 0. Total work done is equal to 0. So total work done you can show with a closed line integral. So we write closed line integral f dot dr equal to 0. And you may be knowing that using a Stokes theorem, you can expand this line integral, and that will give you closed line integral f dot dr equals to surface integral del cross f ds. Understand? So since left hand side is 0, right hand side should also be 0. Or in other words, you can write del cross f equal to 0. That in simple terms does mean that if a force field is conservative, then its curl will be always equal to 0. F can be a mathematical function, but its properties of conservative nature, then its curl will always lead you to 0. That's an important point, valid point. And so you can write del cross f equal to 0. And similarly, if a force function's curl is 0, then that force function can be written as the negative gradient of a potential force. Understand? If a force function's curl is 0, then that force can be written as negative gradient of a potential force. Where f is a function of x, y, z. That is why energy is also a function of x, y, z. Or even you can write in a one-dimensional case, negative grade u of r, if x, y, z is not there. Again, we have non-conservative force. In a non-conservative force field, work done to move a body from one point to another point is dependent of the path. Okay, path dependency is there. In that case, work done in different paths, L, Q, P, etc. will be different. That is why this is shown with an inequality. They are not same. So work done to move from one point to another point, or 1 to 2 and 2 to 1 are not always same. So you cannot add it. There are so many examples for non-conservative forces. Okay, frictional force is a very good example, and similarly viscous force. Okay, whenever a body is moving through a viscous fluid, the body experiences a force that is also a non-conservative nature. And so there are so many other examples for non-conservative force field. Here comes our final topic of this module, that is work energy theorem. It is also connected with our conservation of energy principle, conservation laws. It falls under the conservation laws. So it goes like this. Whenever a body is moved from one point to another point, you express the work done as W12 equals 1 to 2 f dot dr. Okay, it's the work done to move from point 1 to point 2. And here, force is actually mass into acceleration, and acceleration is nothing but a rate of change of velocity dv by dt. So we replaced your force here with mass into dv by dt. Okay, so you can see now dr is there. Dr is nothing but velocity times dt. So dr replaced with v dt. Okay, now dt you can cancel. Okay, here both dt coming. So on cancelling, what we get? Simply W12 equals integral 1 to 2 m v dv. Okay, but mass is a constant. I can take the mass outside. So we have simply a integral x dx term remaining. Integral x dx will give you x square by 2. Similarly, here x is vector v, so v dot v square by 2. Okay, so we have the limits 1 and 2. So you can apply the limits. So what we get? Work done to move the body from 1 to 2 is e mass by 2 into v2 square minus v1 square. Okay, and usually call take kinetic energy of mv square as kinetic energy equal to T. So you can replace these terms with the T1 and T2. What we get? So what we get? W12 equals T2 minus T. Okay, difference in the kinetic energy. So initially you can assume that it had a kinetic energy. You applied some work, you gave some work, so obviously its kinetic energy may increase. So that is the meaning of W1 equals T2 minus T. A change in kinetic energy. Okay, the work done here equals the change in kinetic energy. Now we know if a force is conservative, you had already done its closed line integral of work done around a closed path will equal 0. So, and in that case, you usually write force as a negative gradient of a potential. In this case, we took it as V. And for a one-dimensional case, we usually write force equals gradient of V by dr. Delta V by delta R, negative delta V by delta R. Or you can simply rearrange it with taking total differential. You can write it as F dot dr equal to minus dV. Okay. And already you have work done equals total integral of minus d, because this is integrated. This is a small work done, and total work done from moving from 1 to 2 the integral 1 to 2 minus dv. So you have this minus, if you integrate it, you have v2 minus v1, you have a negative side outside. So this is your work done in terms of potential. In terms of potential, you can write the work done as this. Okay. So initially we had a W1 equal T2 minus T. In the previous case we have seen. So since both are same, you can equate it. T2 minus T1 equals minus V2 minus V1. So what we get? You just rearrange this equation. You get V1 plus T1 equal V2 plus T2. Okay, so always V1 is potential part and T1 is kinetic part. So always you see that wherever the particle be, whether irrespective of the point 1, 2, 3, wherever, always the sum of the kinetic and potential energy is a constant. So this is again a conservation law. So it says like this: the total energy T plus V of a particle is always conserved. Okay, always conserved. So I hope the ideas are clear. We discussed the introductory ideas because these are essential for the subsequent discussion of other theories. That is why this that is the importance of this module. And hope the ideas are clear to you. You watch the video thoroughly and then try this assignment. Here is a question. Find the conservative oblique non-conservative nature of the following force. A force is given in its mathematical form. You have to prove that, or you have to predict that whether this is a conservative force or a non-conservative force. Understand? Very simple. You take the del cross, you can get either a zero value, either a non-zero value. And of course, the del cross part you can expand in the form of a determinant, as usual. Expand the determinant then and check whether that is giving a zero value or a non-zero. Depending on that, you can predict whether it is a non-conservative or conservative force. Another problem is also there. The position vector of a particle, of mass m moving along a circular path is given by this equation. Okay. So prove that the force acting on the particle is of conservative nature. Okay. So again, you have to prove whether this is conservative or non-conservative. How you will prove? R is given and its mass is also given. First, you find the expression for force. Very simple. R is given, so obviously you can find the velocity, and if you can find the velocity, you can find the acceleration. And the force is equals mass times acceleration. So you get an expression for force. Okay, then find the curl of that force and check whether you are getting a zero or a non-zero. That is the only way to prove whether the particle is experiencing a conservative type of force or a non-conservative type of force. Hope these guidelines hints will help you to do the problem. Do the problem neatly in A4 sheets and take the scanned copy of the problem and upload in the Google Classroom. Okay, your your timely submission of the solved problem in the Google Classroom will give you marks. Okay, these marks are very valid. For these marks are used to assess your internal assignment problem. These marks will be counted in the internal assignment. So please do it systematically and upload. Have a nice day. Thank you all of you.